Martha, good afternoon. I don't know where other people are. There's a graph I forgot to mention about. Variation of binding energy per nucleon with mass number. Or with mass. As they come, let me sketch the graph. Team, you're welcome. I wanted to first share a concept on how to interpret this graph of binding energy per nucleon against mass number. And these are the key items on this graph. Now, first of all, we need to understand one thing. Binding energy is a measure of the binding energy per nucleon is a measure of stability of an atom. Can be used as a measure to determine the stability of an atom. Binding energy per nucleon can be used as a measure to predict the stability of an atom. So we can get to know which atoms are more stable when we use their variations of binding energy per nucleon to their different mass numbers. So binding energy per nucleon can represent the average amount of energy needed to remove a nucleon, i.e., it represents the average amount of energy required to remove a nucleon. Now, the mass numbers of the of the naturally occurring nuclides varies between 2. You see this one has mass number 2. So it varies between 2 and 238. So this is what? This is the hydrogen atom. And then this one is uranium-238. So another note we should note on this graph is the mass number I was mentioning the other aspect about the description of the graph, which was saying the mass number varies from the mass number of the naturally occurring nuclides. Mass number of naturally occurring nuclides. Of 2 to 238. You see the last one here has mass number 2. Also the last one up there has mass number 238. Then also the other one we can mention is the intermediate nuclides. It is composed of intermediate nuclides. And these intermediate nuclides include, 1, we have iron up here, iron mass number 56. We have oxygen 16 here. We have here nitrogen 14. We have lithium 6. So the intermediate nuclides, e.g., iron 56, have the largest binding energy. Have the largest binding energy. Note these extremes with the biggest mass numbers, as one might assume. Yeah. Why? They have the largest binding because they have the largest binding energy per nucleon, and therefore they are more stable. Because they have the largest binding energy per nucleon. Hence, they are more stable. The other thing to mention also on this graph is that the small values of binding energy per nucleon, the small values of binding energy per nucleon for higher and lower masses or lower mass numbers imply that these nuclides are relatively unstable. What does this statement mean? That those items which have smaller mass numbers or smaller values of binding energy per nucleon For high mass numbers and for very small masses, it implies that those nuclides are relatively unstable. Okay. Then there are sorts of for those nuclides we are talking about with small masses and higher masses, which have a small value of binding energy per nucleon. Those nuclides, you see that their potential source of energy are reactions which involve disintegrations. And remember the reactions we have talked about, fission and fusion. Eh? So whenever we have a reaction of disintegration of their nuclides, or for example, disintegrating a heavy nucleus into lighter nuclei, or merging smaller nuclei to form one big amalgamated nucleus, then that's where their source of energy can be, by only making sure that we disintegrate them or we merge them, depending on their sizes. So you can say more on that, i.e., their potential source of nuclear energy, their potential source of nuclear energy are reactions involving fission or fusion of particles to produce a nucleus of higher binding, energy and nucleon. Hence, become stable. So, with this, it implies that small values of binding energy per nucleon for higher or lower mass numbers imply that these nuclides are relatively unstable. So to stabilize them, we get to know that one, their potential source of energy comes from reactions which involve either fission or fusion of particles to produce a nucleus of higher binding energy per nucleon. When they produce nuclei of higher binding energy per nucleon, then they will become what? Stable. Otherwise, they will remain unstable if they do not undergo fission or fission. So I wanted to comment on that graph. I had missed it out. No matter you've come with bad network. So with that, today I want to advance and talk about X-rays. I want to review X-rays. Who can define for us what X-rays are? What are X-rays? Someone please define for me X-rays.
Electromagnetic.
Yeah?
Electromagnetic.
No, we can't hear you. X-rays are?
These are electromagnetic radiations emitted from a heated.
These are electromagnetic radiations or waves produced. X-rays are electromagnetic radiations produced when fast-moving electrons are stopped by a hard metal target. Okay? So one, we have production of these X-rays. We need to understand how the X-rays are produced. Production of X-rays. This is done in what we call an X-ray what? Tube. The X-ray tube disturbs you to draw. You can sketch the one for O level. But to start with, we need to know that one, the X-ray tube has a filament which is heated at a low tension. Then we have a focusing cap. On this side, we have our target. So a beam of X-rays comes, strikes the target. Then what we produce is X-rays. We have lead shells, which we use as protective measures for the person operating the what? Then we have an extra high tension that is connected between the anode and the cathode. We have these as cooling fins. These are X-rays. The focusing cap. This is the filament cathode. Evacuated glass envelope. This is extra high tension. And now remember that when we are marking these, this is beam of fast-moving electrons. You can say beam of cathode rays, because cathode rays are beams of fast-moving electrons. Then this is the anode. Now, when you ask such a question, one, someone has to be in position to sketch the diagram appropriately, and at least you label 3 correct parts to get the 2 marks for the diagram. You label any 3 correctly, then you sketch the whole diagram correctly. When you sketch the whole diagram correctly, it's half a mark. Then each other parts will be given half a mark. For example, if I was to mark this, I would come and give this a half a mark, this a half a mark, and also give this one a half a mark. Then also the diagram itself a half a mark. So that's what makes the 2 marks for the diagram. Now, having sketched the diagram, one should know how the procedure goes. We make a lot of errors in writing this experiment. But it is very rare for a question on X-rays to be set and there is no part of production. So to start with, a filament is heated. This is the filament we are heating. We are heating it so that it can eject what? Electrons. But it is heated by a low voltage supply, this one. Sometimes some books have low voltage. Others, they say low what? Low tension. Low tension means low voltage. So the filament is heated by a low voltage supply, LT. And what happens? It heats up. When the filament heats up, electrons are going to be produced. How do we produce electrons when they are coming from a heated item, or a heated metal, or a heated cathode? How do you produce electrons from a heated item? Someone answer that. Hello? How do we produce electrons from metals when they are heated? Martha. Guys, are you there?
Yes.
Yes, how do we produce electrons when they are heated from a metal surface?
By Munich Emission.
We produce them by a method or by a process called thermionic emission. So by definition, thermionic emission is the emission of electrons from metal surfaces when they are heated to high enough temperatures. Now, here when you heat the cathode with a low voltage supply, you're going to produce electrons by thermionic what? Emission. Now, these electrons are going to be focused by the focusing cap, yeah? And then, because of the extra high tension between the cathode and the anode, this extra high tension is going to produce a potential, which potential will accelerate the produced electrons. So the produced electrons gain kinetic energy and travel at very high speeds to come and meet the target anode. Now at the target anode, what is going to happen is most of the energy these electrons are coming with is going to be converted into heat, which will be cooled by either oil or water running through the cooling fins, while a very small percentage of that energy is going to be converted into X-rays. So with that, the X-rays can be produced. Now, I've seen some people commit themselves. Yeah? I've seen people writing, instead of saying a very small percentage of the energy is converted to X-rays, people say almost 1% of the energy is converted into X-rays. 2%. My friend, when we start calculations, you'll get to know that total energy may be 98% of the energy, maybe 99.9% of the energy, maybe this. So it means it is not a constant value. But if you overcommit and say 1% of the energy, 2% of the energy is converted to X-rays, it means that every X-ray tube we operate, 2% is converted to X-rays, which is not the case. Remember, we vary them to produce soft X-rays and hard X-rays. We vary them to produce many X-rays and few X-rays. You get it? So do not commit yourself with that percentage, but rather say a very small percentage of the energy is converted into X-rays, while the biggest percentage is converted into heat. So let's outline the procedure in bullet form. One, we are saying you heat the filament with a low tension supply. What happens next? Electrons are emitted how? Thermionically. 3, emitted electrons are accelerated by the extra high tension between the anode and cathode. Another one, when fast moving electrons reach the anode, a very small percentage of their kinetic energy is converted into X-rays. And their biggest percentage is converted into heat. The biggest percentage of Ke is converted into what? To heat, which is cooled by oil or water running through cooling fins. I forgot maybe one thing here, the focusing cap. When electrons are emitted thermionically, the focusing cap focuses the electrons to the target. So with that, we shall have produced our what? Our X-rays. Then also remember that when electrons, it is the energy of the electrons that we convert. We do not convert the electrons themselves. Some people say the electrons, when they reach the target, they are converted into X-rays and they are converted into heat. No, but we convert their energy because radiation is energy. So X-rays are energy, they are electromagnetic radiation. EM is energy. So we convert the energy of the incident electrons, converting that energy into heat, because you know energy conservation, you just transform it from one form to another. Into heat or into X-rays. But a very small percentage is the one which goes to X-rays. Then it is from there that also we can talk about what we call X-ray spectra. Okay, let's talk about their properties first of all. These ones, I think we could mention them just. Can you mention some of these properties? Also mention their uses. These ones just share. Someone give me one of the properties of X-rays. You know. One. They what? Are you giving us one? Guys, properties of X-rays?
Have no.
They have no
Charge.
Charge. So if they have no charge, they cannot be deflected, reflected, diffracted, but they can be diffracted. By electric, no, they can also be they cannot be diffracted by electric, magnetic, and electric fields because they possess no charge. Another property?
They travel in a straight line.
They travel in a straight line. Another one?
High penetrating power.
They have a what?
High penetrating.
High penetrating power. High penetrating power, all EM penetrates, but if you're saying they have a high penetrating power, then you're comparing them with something. Because their penetration power can be varied. If you go to a hospital, the X-rays they put in you, or they try to direct into your tissue to see whatever your body is all about inside, depends and it varies. Yeah. Well, that's why they sometimes have to measure our body size, our weight. They measure our age. Then they can get to know the variation of the X-rays they're supposed to pass through your body. Okay? Travel in a straight line, travel at a speed close to that of light. I think we know that one, though you had forgotten. It affects photographic plates. If you have been in position to go to hospital, or your parents have been to hospital and they come back with what we call a photographic plate. In vernacular, that chifanany is called a photographic plate in science, physics. So they are affected by X-rays. Also, X-rays can cause fluorescence on some materials. More so, X-rays, because they are electromagnetic radiations, when they fall on metal surfaces, they can also eject electrons by photoelectric emission. Okay? So all those highlights, please, you can have them down if you don't remember them, or you revisit your notes to have a better recap of what you had discussed in terms of properties earlier on. They can penetrate matter, but they can be stopped by lead shields or by lead. That's why in hospitals, the people who operate the X-ray machine, they wear protective garments. They wear protective coats. Those protective coats are quite heavy because they are coated with lead. So when they are coated with lead, the lead protects them, protects the X-rays from penetrating into their bodies, since they are not the ones who are actually being examined. Otherwise, if they overexpose themselves to the X-rays, they will ideally get into a position of causing cancer to their bodies, and then the X-rays might end up burning some of the cells, bringing cancerous cells to their bodies. X-rays can also be diffracted by crystals, leading to an interface pattern. So basically, those are the properties of X-rays. Then can we talk about also the uses before we can go for the spectra? Uses of X-rays. I don't know how many of you have been to the X-ray machine. I, for one, I don't remember. I've been in a CT scan, but an X-ray tube, an X-ray machine, no. But it can be used to detect fractures of broken bones. Of course, I've never broken my bone, but whoever has broken a bone, you've ever gone to an X-ray machine and they inspect exactly what happened to your body. And how they do that is that if this is the bone, and it got cracked here, what happens is X-rays can pass through flesh, but they don't pass through the bones. So what happens, they will blacken all these other parts where bones are not found. They will blacken all those parts. Now, they will also blacken this part here between the bone. So when this part is blackened, that will confirm that the leg is broken. Otherwise, if they check and they see the bone is still in the same shape, is still continuous, there is no crack anywhere, it means this person's leg is not broken. Maybe it was just put into tension. So that's how we can use X-rays to predict whether someone has a fracture or not. Another use we can have, it is used for treating cancerous cells. How do we treat cancerous cells? We direct the X-rays to the cells which have cancer and we burn them. If your parents, you ask them, they used to have that saying, they knew the older people before who used to get cancer. They used to say, okubakalirira. Okubakalirira meant going to the cancerous institute. Then they direct X-ray radiation to those cells only which are affected. Yeah? But they vary the X-rays. They're not the same X-rays which pass through you when they're just investigating your body. So the X-rays which used to treat cancerous cells are different. So that's why I say the other point you mentioned, when you're saying a small percentage of X-rays, instead of someone committing to 1%, look at how people now vary X-rays. They can vary the magnitude of X-rays being directed to a point so that we can burn cancerous cells. So they can be used in treatment of cancer by burning the cancerous cells. Another importance also of X-rays we can have is they can be used to detect alterations made in artwork. When you see these big billboards, which are put on a big canvas of a casing. So they use X-rays to predict whether the images drawn, whether the paints drawn, put on on that canvas are all bringing out the illustrations as predicted. Wow, rain wants to interfere with my best network of today. X-rays can be used in the study of crystals. Yeah, we can use X-rays to study the structures of what? Of crystals. Then we can also have X-rays can be used to detect cracks in metal castings and welded joints. There are those metals which we join, or those tubes we join. Now they can use X-rays to pass through them, and then they can predict where we have either a crack or a leakage of a given pipe. Then also finally, we can also use X-rays to predict or to determine any foreign bodies or foreign particles in a human body. For example, you have been under an operation. If the operation was intense, and maybe they forgot some blades in your stomach, in your body. We can use X-rays. They use X-rays to scan the entire system after an operation. But of course, apart from the village hospitals, but in town hospitals, that is expected. After a thorough operation, they need to pass through X-rays through your body to see if there is any metal, to detect any metal. So they can be used as metal detectors in human bodies after operations. So with that, they avoid the risk of you going to sue them in court that they forgot the blades in your body. So those are some of the uses of X-rays. Last, we can talk about their hazards. Hazards of X-rays. One, they can cause deep-seated burns. That is, if they expose hard X-rays to you. Hard X-rays are X-rays produced by electrons of very high kinetic energy. And how do we get those ones? We get those ones by varying the extra high tension. Yeah, when the extra high tension is big enough, we are going to have a very hard X-ray produced, because electrons will be traveling very fast with high kinetic energy, which high kinetic energy is converted into hard X-rays. When you reduce the extra high tension, you will produce what we call soft X-rays. So they can produce such wounds. Two, they can cause cancer again. How? They can cause cancer if overexposed to someone's tissues or someone's body. If you're a person working in an X-ray tube or in an X-ray room, you don't need to work there for more than 7 years. That is the prescription. After 7 years, you stop working there, look for another job. Why? When you get exposed to them, risks are there of getting exposed to them. You can start experiencing cancer as a result of the X-rays burning some new cells to cause cancerous what? Cells. Now, before, people who used to go for what I call the kubakaririra, who used to go and they burn cancerous cells. Some people used to fear going there. Do you know why? They used to say, when people go for those things of kubakaririra cancer, cancer spreads very fast and they die very fast. Now, the science behind it was local. The locals were interpreting science in vernacular. This is what could happen. In actual sense, what could happen would be, when they go to burn these cancerous cells, they could overexpose the X-rays to the cancerous cells, so the cancerous cells could die. But in the process, the operators could risk and also burn new cells. Now, whenever they burnt new cells, the new cells could spread the cancer very fast compared to the old cells, because they have more kinetic and they had more energy. So at the end of the day, someone with the cancer would eat him up very fast. So that's why people in the past years would fear now going for burning of cancerous cells. So that is also risky. It's a hazard that sometimes people reach a point and they overburn the cells, but as they overburn them, they risk and burn other new cells, which brings about new cancer in someone's body. Another one is X-rays can cause mutation. Of course, cancer basically is coming from what? From abnormal what? Who is offering biology? Namata, tell us, what's cancer? What brings about cancer? There is abnormal growth, I think, of what? Of cells. Yeah? So, in the abnormal growth of cells, we can end up having what we call mutation. So, your body can end up mutating because of the cells being burnt in any way or the other. Now, before I will go to the, even if I don't go there today, there is the aspect I need to mention which confuses us so much. The good thing with this aspect of X-rays, from the definition there up to where we are, you just need to understand the science behind. You need to end up feeling the science flow, the physics flow in your head. With all that I'm explaining, it should be flowing in your head. If you have a concern, you raise it. Now, there is what we call intensity and we have intensity and, or sometimes we say we have what? There's another one I've forgotten. We have quality and the quantity of X-rays. This one is intensity and what? And penetration power. Is it? Intensity and penetration? Penetration what? Power of X-rays. These two questions are the same. How do they become the same? For example, intensity talks about quantity. Then penetration power talks about the quality. Now let's talk about each and every one of them. Let's start with quantity. Quantity of X-rays depends on what? The number of X-rays we have. How many X-rays are you producing? You need to go back to where they come from. Where do X-rays come from? X-rays come from fast-moving what? Electrons. Where do these fast-moving electrons come from? They come from the filament cathode. It's better you work backwards. You start from here. X-rays, we want very many of them. Where do they come from? From here. Where do they come from to reach here? From here. Where does this come from? From the extra high what? Tension. I don't know that you're getting my physics very well. I want you to understand this point, that you can get this interpretation of quantity by reversing backwards up to where they originate from. So to start with, we have said quantity determines number. So the number of X-rays, if I want very many X-rays, now remember, for you told me 1%. Those of you who write 1% and commit. That's why I said we should not commit. We are here now saying, how can we increase the number from 1%? How can we increase the number from 2% of the energy converted to X-rays? How do we get the number to be 5%? You get it? Now to do this, you go backwards and look for where it starts from. We are saying that the number of X-rays depends on the number of electrons striking the target per second. But this number of electrons striking the target per second are produced from the, or come from the number of electrons thermionically being ejected by the metal, by the filament cathode. But this filament cathode has no control of electrons apart from the low tension supply that has been applied to it. So that's where the physics is. Okay? So the quantity of X-rays depends on the amount of low tension supply. The low voltage supply predicts the quantity of X-rays. So if I want more X-rays, I increase the low tension so that it heats up more the filament cathode. When the filament cathode is heated up more, what happens? More electrons are going to be produced thermionically per second. And what will happen? Very many electrons are going to run and strike the target per second. And what will happen? A very small percentage of their energy is converted into X-rays, but this would be bigger than what we had before. Reason? We have more electrons coming in. If initial electrons were 1 million striking the target, I increase the low tension by doubling it. Perhaps it gives me 2 million electrons. Then, if only 1% of 1 million is what? 1% of 1 million is 10,000. If only 10,000 X-rays, photons, were being produced, yeah? Then when I do use 2 million electrons, you see that I'm going to have 20,000 for extra photons produced. So there I would have increased the X-rays by varying the extra high, by varying the low tension at the filament. So basically, the quantity of X-rays depends on the amount of the voltage applied at the filament cathode. Then let's go to quality or penetrating power. So quality of X-rays. The quality of X-rays depends on the quality, of course, the quality, look at it in this picture or in this form. That quality would imply how good are the X-rays you have. How strong are they? How much deeper can it penetrate somewhere? That's why we relate penetration power with the quality. Now, this one comes in with them having very good energy. So it means the electrons we produce must be having a very good, sufficient energy to end up giving us a very good quality of X-rays. How do we do that? We do that by variation of the extra high tension. By varying the extra high tension. When you vary the extra high tension, you're going to give a very high potential relative to the cathode, between the anode and the cathode, and the electrons will move at a very high kinetic energy. When they move at a very high kinetic energy, that very big kinetic energy, if we were converting 2% of the energy, if initially 2% energy was maybe, if it was initially maybe what? 1,000. 2% of 1,000 is almost what? Something like 20. Now, if you increase the energy to 10,000, then 2% of 10,000 becomes 200. Okay? So you will see that the electrons will now travel with a percentage of 20, a percentage of 200 joules, which 200 joules is going to be converted to X-rays. So definitely we shall have X-rays of higher energy. We shall have X-rays of higher penetrating power. We shall have X-rays which we call the hard X-rays. Now, it is from here that we end. That's why sometimes this question is in three forms. 1, intensity, penetration power. 2, quality and intensity and quantity. 3, they can bring it in form of soft X-rays and hard X-rays. Explain how soft X-rays are produced. Explain how soft and hard X-rays are produced. There they're asking you for quality. They're asking you for penetration power. How would we produce good quality X-rays that penetrate either so deep or so small? So the question is rotating about quality. If it comes in terms of soft and hard X-rays, if it comes in terms of penetration power, if it comes in terms of quality. While quantity and intensity, those ones are predicting the size or the number of X-rays that you can produce. So with this, if they ask you to produce or to tell us how we can produce soft and hard X-rays, soft X-rays are those X-rays which have a very small frequency, but they have a very long wavelength, while hard X-rays are those ones which have a very small wavelength and have a very high frequency. Now, in this regard, because this comes from the formula energy is equal to HF, which is equal to HC over lambda. So energy to be biggest, maximum, you need to have minimum wavelength. So minimum wavelength, these ones produce hard what? Hard X-rays. While these ones which have minimum energy have HC over lambda maximum. These ones produce what we call soft X-rays. So the ones they use in hospitals are soft X-rays. The hard X-rays can be used in industries and factories. They can be used in cutting metal. But they need a lot of energy for that. So they use electromagnetic radiation with minimum wavelength. That's why when we come to look at what we call X-ray spectra, we shall have what we call cutoff wavelength. Yeah? But since we're not talking about that yet, let us first concentrate on this one. I was saying soft X-rays and hard X-rays can be predicted using 1, the quality of X-rays you produce, and we have seen the quality is brought about by varying the extra high tension So if you want to get a very good quality of X-rays, if you want to get very hard X-rays, just make sure you increase the extra high tension between the anode and the cathode, so that the electrons move at a very high speed, or when they move at a very high speed, they will move with very high kinetic energy. On reaching the target, they will lose a very good amount of energy, which will induce production of hard X-rays. Then the reverse is true. If you want soft X-rays, then reduce the extra high tension, the EHT. I wrote ETH, it's supposed to be EHT. Reduce the extra high tension. When you reduce the extra high tension, these electrons will reach the target with a low energy. So they will produce X-rays which are not having very high energy. So those X-rays will be having a very low penetrating power. Those X-rays will be having minimum danger to human tissue. Yeah. So all this is about, these are basically all, these are word explanatory science concepts that we have been talking about. So with those illustrations I've mentioned, do you have any questions? Can I have any question among the items I've mentioned? If there's an explanation that you've not got right, please let me know so that I can rick it up before we can advance to anything. Or even our time is almost done. But I need a question before you can leave. If there is someone who doesn't have these notes, you let me know. And I can send you some of these notes. Make a write-up on your own. Any questions? No questions. Let's finish up with the spectra, so that next time we shall start with X-ray diffraction. Oh, before even X-ray diffraction, we shall start with some small calculations on production. Then after we shall go to X-ray diffraction. So I want to discuss X-ray spectra. Of course, if there are many, they are called spectra. If it's one, it's called spectrum. Eh? Now, there are two types of spectra. One, we have what we call the continuous spectra. Then two, we have what we call the line absorption spectra. Who can remind us of what these spectra talk about? Anyone who recalls what a continuous spectrum is all about? Hello? So these are the two spectra for X-rays. And these two spectrum for X-rays, basically, they depend on this. One, the continuous spectrum depends on multiple collisions of the electrons when they collide with the target atoms. When these electrons make multiple collisions with the target atoms, time comes and what they do is they make these collisions, and some of them end up penetrating so deep into the nucleus of the atom. And then they knock out the innermost atoms from the innermost shells. Innermost electrons from the innermost shells. Now, as a result, when these collisions are taking place, we end up emitting X-rays of different, my bad, rain has come. This time seriously. Let me just get my umbrella. What do you want? It has been putting me on a lot of pressure, but now let me get my umbrella. In case it comes back again, I'll just not leave just like that. Okay, so I was saying, we have two types of spectra. One, we have what we call the continuous spectra, and then we have what we call the line spectra. The continuous spectra comes from continuous continuous or multiple collisions of the electrons with the target atoms, yeah? While with the target atoms, and the speeds of the electrons end up getting decelerated. So they go on, as they collide more and more with the atoms, they are decelerated. So they go on reducing what? Their velocity, and they go on reducing their energy. So with these different amounts of energy lost, X-rays are given off, ranging from a given wavelength to a maximum, okay? Or varying X-rays are given off with varying what? Wavelength. So we have what we call wavelength. Lambda is the wavelength. So as collisions take place, we shall have varying wavelengths from a given value to a maximum. But the maximum wavelength gives you the minimum energy, while the minimum energy, lambda, gives you the maximum wavelength. So if this is maximum, this will be minimum. While if this is maximum, Hc over lambda, this will be minimum. Then the line spectrum is also quite interesting. In which way? The line spectrum comes as a result of having electrons penetrating so deep into the nucleus of the atom. And then, boom, they knock out an electron from the innermost shell. So for example, if this is the nucleus inside the atom, then we have an electron here, we have another one here, we have an electron there, electron maybe there, electrons here, there, there. Hope you remember your electronic configuration and chemistry. Now what happens is, we are going to come and boom, we knock out this one. An electron which is coming, comes and knocks out this. When it knocks out this one, it is going to create a gap. When it creates a gap, what is going to happen is, the electron is going to remain unstable. Initially it was maybe stable, but when this electron came and knocked out this electron, the gap which has been left here now needs to be filled. So when the gap is left, the atom becomes excited and unstable. When it becomes excited and unstable, what is going to happen is electron transition is going to occur. Electron transition maybe can occur from there to come and fill the vacancy left. When electron transition occurs, remember from Bohr atom, the structure of an atom, that electrons do not emit electron energy when they are revolving around the orbits. But when they make transitions from one energy level to another, they will emit energy which is defined by E is equal to HF. So it is from here that the electron will jump from a higher energy level to come and fill the vacancy left so that it can stabilize the atom again. When it comes to fill the vacancy left, transition is going to occur. As electron transition takes place, it occurs with emission of energy, which energy is going to be an X-ray photon, which is in form of lines. So it will be in position to form what we call a line spectrum. So let's highlight those points, unless if someone has a question on the items I've mentioned. But if no questions, let's highlight the points. 1, continuous spectrum. What have we said about a continuous spectrum? It is formed as a result of multiple collisions of electrons with what? With the target atoms. That's 1. The electrons become decelerated. The electrons become decelerated. What happens? They lose energy. Different amounts of energy are lost. What happens next? When they are lost, what happens? X-rays are given off. Of varying what? Wavelengths. Of varying wavelengths. These wavelengths will vary from what to what? They will vary from a minimum value to infinity. The X-rays produced have varying wavelength from a minimum to infinity. So those are the key points about continuous spectrum. Multiple collisions of the electrons with the target atoms. Electrons become decelerated, so they lose energy, and the energy lost, as we lose energy, they give off different X-ray photons of varying wavelengths, and the X-rays have varying wavelengths from a minimum to maximum. So we can have the line spectrum. The highlights for the line spectrum include what? Actually, this wavelength is what we call the cutoff wavelength. I've forgotten. That minimum wavelength is what we call the cutoff what? Wavelength. Here, highly energetic electrons penetrate deep into the nucleus. What happens? Knock out an electron from the innermost shell. What happens when an electron is knocked out? When it's knocked out, it's either ejected completely out of the atom, or it can be knocked out to go and fill a gap in the higher energy levels. Knocked out from the innermost shell, the electron is either taken out completely or goes to higher energy levels. What happens if vacancy is left? Vacancy is left. in the inner shell. When a vacancy is left, this puts an atom, putting an atom in excited state. When it is in excited state, what happens? The atom becomes unstable. When the atom becomes unstable, the subsequent electron transition from high energy levels causes electron transition occurs. When it occurs, causes X-ray, photon, of definite wavelength to be emitted. And this emitted energy, the energy of the emitted photon, the X-ray photon has energy equal to the difference in energy at the different energy levels. So this is idea going to be E is equal to E1 minus E2. I mean E2 minus E1, where E2 is the energy in the high energy level, then E1 is the energy in the lower energy level. So with those explanations, guys, you need to summarize all that we have discussed and ensure that you can have them well sorted and catered for. Okay, any questions? Any questions, guys? Please, these explanations, when it comes to discussions, you should be able to handle them. Yeah? Anything they ask you about these, they ask you why, how does continuous X-ray come about? You should be able to handle. How does cutoff wavelength come about? You should be able to handle. Cutoff wavelength, by the way, is brought about by producing the most energetic X-ray photon. Remember, I told you energy is equal to Hc over lambda. So to have maximum energy here, you have to have the minimum wavelength. So lambda minimum is what they call the cutoff wavelength. So the cutoff wavelength is produced when you have produced the most energetic X-ray photon of maximum frequency, corresponding to lambda minimum, which is called the cutoff wavelength.